This is our AE 1601 glider final report by Nicholas Roberts
and Bella Diedrich. For our project description, we had to design, build, and flight test a small glider made primarily from balsa wood, which we were given, and we were encouraged to be creative, and the end goal was to fly 20 feet at least, and in the tournament fly off, possibly win, but most importantly, have fun. We had 3 deadlines. The first was November 4th for the first checkpoint, the second was November 13th, and the flight day was the 18th.
Our project requirements and measures of success. We had to design using principles of wing aerodynamics, and we had to do research before and during the design process with reliable sources. We had more than 50% of the weight had to be balsa wood, and we weighed the components to determine the weight. It had to fly at least 20 feet, and we measured on the CRC Gym for the distance and accuracy. We made sure there were no sharp points in case it hit a person, and we sanded the edges to avoid injury. We made sure it was 16 by 16 inches, so it could fit in the 16 by 16 inch box. And we measured with the tape measure. It had to remain intact for flight in order for it to count, so it couldn't break or splinter after a flight test. And there had to be no mechanical parts or active remote control. And we had to have a max of 2 sets of laser cut wings, a horizontal and vertical tail, and it was monitored by the AMS.
For alternative generation, we came up with a few different ideas that we traded. The first was a T-tail. It was good because it would have increased flight distance, but it's not very effective on the small scale and with such a low angle of attack. So we ultimately didn't use it because it would also increase build time. The tapered wings would have reduced drag and increased lift, but it required an increased width of the wings, and we didn't use it because we had a 16-inch constraint on that. For the neutral wing angle, it would have been easier to glue and less likely to break, but we wanted to maximize flight distance, and that's why we didn't use it.
For the probability of success, the T-tail had a medium probability of success of about 75%. The tapered wings had a very high probability of success, about 90%. The neutral wing angle had a low probability of success of about 65%. The T-tail was medium because T-tails are only useful with high angles of attack, so there was too much uncertainty in flight. And the tapered wings had the highest probability of success because wing shape in general most affects performance, and the tapered shape is very effective. And the neutral wing angle was the lowest probability of success because when having no angle on a glider, the stability of the glider is greatly reduced.
For the design process, we first had to understand the requirements and what we were given. Then we had to do some research and brainstorm some initial ideas and generate alternatives for them. Then we selected an idea to build our first prototype. We had to test and evaluate and redesign or reiterate. And then this is us communicating the final result.
Our balance and center of gravity. So for the first iteration, the wing was about 6.875 inches behind the nose, which meant that the center of gravity was slightly behind the wing. For the second iteration, we moved the wing up by about 0.75 inches to move the center of gravity up. And the final iteration, the center of gravity was at 5.5 inches from the nose after we added the clay. The chord of this elliptical wing is about 2.75 inches. So a quarter chord would be 0.6875 inches from the leading edge. And based on hand balancing the glider, we found our center of gravity to be located 1.375 inches from the leading edge of the wing, which is a little bit behind a quarter of the chord.
For lift and drag calculations, we first took the weights, the planform area, and the width of our wings and converted it to pounds and then feet squared and feet. I took the average velocity of 3 of the trials to get the average as 13.09 feet per second. And then I used this to calculate the coefficient of lift based on the equation that we were given, and that came out to 0.626. Then I used that to calculate the induced coefficient of drag to be 0.0249. And then, of course, we needed total drag coefficient, so we were told to equate the zero drag coefficient and the induced drag coefficient, which were both 0.0249. And then when you add those together, you get 0.0498 as our total drag coefficient.
Our design iterations. Our original design had a T-tail and elliptical and dihedral wings. As you can see on the right, you can see the top, side, and front view of our first design. We made 3 iterations along the way. The first iteration was our initial design with a conventional tail setup, no ballast, and after we flew and tested that one, we figured out that it flew to the left and did a backflip. So our second iteration, we moved the wing forward by about 0.75 inches in order to move the center of gravity up so it wouldn't do a backflip. And then we added clay on the left wingtip and on the front of the wings for the third iteration once it did that again. So you can see the final iteration in the top picture.
Our final measurements, from tip to tail, the fuselage was 14 inches, and then the width of the wings was 15. So of course that's within the 16 by 16 box. The mass of the clay was 5 grams, and when combined, the total mass was 13 grams.
And this is our video.
So for an overall summary, we ultimately had success. Our final distance, the furthest that we threw, was 62 feet. The first throw we did for the tournament is 20 feet, so we didn't make it to the next round. And while we were practicing, both wings broke, so we had to glue last minute. But we continued throwing after the tournament to find our best distance. And in the future, we want to make some improvements to make the wings more secure.
And these are our sources. We have 4 sources that we used heavily in our research.
Thank you.